As we continue in this chapter with solving for linear systems of equations, we're going to discover that maybe graphing is not the most efficient way for us to come up with our solution. Now remember, a solution to a system of equations is, at least from a graphing standpoint, is the ordered pair that represents the point at which two lines intersect. But we don't need to graph to find that ordered pair. We can use some non-graphing methods, otherwise known as algebraic methods. And the first of those methods we're actually going to practice is called substitution. So substituting just means to replace. So we're used to substituting. Most notably, we're used to substituting variables, whether it be in an equation or an expression with a given value. But what we're going to now start to get used to is replacing a variable with an expression that has another variable in it. Okay, so as we go through this process, we're again dealing with the system of equations, so two equations. And we're going to want to take one of those equations and rewrite it so it is solved for x. Either it's going to say x equals, or it's going to say y equals. And that will allow us to then take that equation and use the expression from it to substitute in for the other variable. I know this sounds confusing, but we'll be able to substitute in for the other variable. And through algebra, we'll be able to replace one variable with another and essentially find our way into solving an equation that has only one variable in it. Now that is nothing more than going back to what we did in chapter 3 when we solved all sorts of equations, one-step equations, two-step equations, multi-step equations, but all those equations only had a single variable in them. So what substitution allows us to do is to get rid of one of our variables and replace it with an expression with the other, so that we can find our way back to using skills that we learned in chapter 3 to solve for essentially half of our ordered pair. Okay? And then we'll work from there to use that information to solve for the other half. So maybe instead of continuing to talk, it would be easier if we just took a look at an example and worked it through. So what we're looking for as an ideal candidate for a system of equations that would work with substitution is we're looking for an equation that has a coefficient for either x or y with a value of 1. So don't forget, a coefficient is nothing more than a number that a variable is multiplied by. So if we look at this first equation, 3x plus y equals 3, the coefficient for x is 3. The coefficient for y, it's invisible to us, but we know that there's a 1 there. The coefficient for y is 1. That's already telling me that's a really good candidate for us to consider for using substitution. This number here, without the variable, we call that a constant. So the constant in this equation is 3. Just for practice, the coefficient for x in the second equation is 7. The coefficient for y in this equation is 2. And the constant is 1. So this equation isn't looking as appealing to me because I don't see a 1 either in front of the x or in front of the y. So this is the equation that we're going to focus on. So we're going to start by following step 1 as outlined above. We're going to solve this equation for either x or y. And the one that we solve for is going to be based on where we see that 1 in front of. So we're going to solve this equation for y. So we're going to start with 3x plus y equals 3. And to simply solve it for y, we're just going to subtract 3x on both sides. What we want to do is to basically get this equation to say y equals. So this is going to say y equals, negative 3x plus 3. Now you might be looking at this saying, hey, this looks familiar to me. This is y equals mx plus b. Well, that's not a requirement. All I really care about is that this equation is solved for y, and it is. It says y equals negative 3x plus 3. So we've taken one equation and we've solved it for y. So here's where the substitution comes in. We're going to take this expression right here and we're going to substitute it for y because it's just another name for y. So we're going to substitute it, but we're going to substitute it not into the same equation that we just rewrote. So we're not going to go back to the same equation here. What we're going to do is we're going to substitute it in for y in the other equation right there. Okay, so as I start to write this new equation, or this second equation, I'm going to start out by saying 7x plus 2. But where I see the y right here, I want to use my new expression for y. So I'm going to substitute it with negative 3x plus 3. And then I'm just going to finish writing the rest of the equation. So there is my substituting. Okay, so I'm going to show that going right there. That's my new name for y. Okay, that's the y that was right there. And now we're going to just do, oh, now look at this. This is our chapter 3 type of equation. This is a multi-step equation. And notice what happened. Our y got replaced with x. And now we have an equation with just a single variable. So we can actually go through that SIS process that we're familiar with. Simplify, isolate, solve. And we can distribute, we can combine like terms, and we can begin to solve. So let's see. I'm going to get 7x. And I can distribute that 2 into the parentheses and blow those parentheses up. Minus 6x, that's the 2 times negative 3x, plus 6, that's the 2 times 3, equals 1. And then I can take it further by combining my like terms. 7x plus negative 6x is x, or 1x, plus 6 equals 1. So I did my simplify, let's see, I need to move on to isolating because I did all my distributing and combining of like terms. So I can isolate this x by subtracting 6. And I get x equals negative 5. And there's nothing to solve here because it's not like there's a coefficient I need to divide by. So what I've done is I've rewritten one of my equations, in this case my first equation, so it says y equals. I took that expression that y equals and I replaced y in my other equation. I substituted y in my other equation with that expression. Down here in the blue, negative 3x plus 3. I used everything I know about solving multi-step equations to simplify, isolate, and solve. And I distributed, combined like terms, isolated, and did any solving I needed to. And I got the value of x equals 5. Now think about what that represents. That's part of my ordered pair that is going to be my solution. In this case, that is my x coordinate. Okay, so what can I do from here? Well, I can take that value, and I can substitute it into one of my original equations, and we'll talk more about the importance of that. I can substitute back into one of my original equations, and since I know x, all that I'm going to be left solving for is for y. So which of the two equations we use, it does not matter, but when I eyeball, I see that the first equation looks a little bit easier because there's not as much math involved. So I'm going to take that equation, 3x plus y equals 3, and I'm going to substitute my x. I'm going to substitute my x because I know that value. So I'm going to say 3 times negative 5 plus y equals 3. And I'll just finish doing the math. 3 times negative 5 is negative 15. Plus y equals 3. And to solve for y, I would naturally have to add 15 on both sides. So y equals 18. So what we did is we first took an expression by rewriting one of the equations. we substituted in, and we solved for half of our equation, or half of our ordered pair. We got x equals. We took that known value and we used it in place of one of our equations for x in this case, and we solved for the other variable. Now those two variables together make up our ordered pair. So our solution should be, instead of x, y, well, our solution is -5, 18. And that should be our end result. That should be, if we graph these two equations, the point at which those two graph lines would intersect. So let's do a quick check if we can. Let's see, our first equation, 3x plus y equals 3. 3x plus y equals 3. I should be able to do 3 times -5 plus 18 equals 3. -15 plus 18 equals 3. 3 equals 3. So check. I should be able to do that check on the second equation. 7x plus 2y equals 1. Let's see. 7x plus 2y equals 1. Well, if I substitute 7 times -5 plus 2 times 18 should give me an outcome of 1. -35. That's 7 times -5 plus 2 times 18 is 36. Does that equal 1? 1 equals 1. Check. So that is the one and only ordered pair that will make both equations true, which means it's the one point that's on both lines, which further means it's the point of intersection for our two graph lines, which means it is our solution. That is our solution. Okay? So you have two examples to work with. I'm going to set you up in both. Now, both of these are fairly easy because this already says y equals. This already says y equals 2x minus 1. So I can take that and I can substitute it in for y and solve for x. This already says x equals, x is isolated, y plus 3. So I can take y plus 3 and I can substitute it this time in for x into my other equation and solve halfway through for x. Okay? If you're confused about any of this, then you should look back at the notes that you filled in here and even look back at this video and pause the video as often as you need to. And we will come back and talk about the substitution process more and practice it more tomorrow in class.